Hello friends. Today in this session we will discuss FAA method of flexible pavement design for airports. FAA here is Federal Aviation Administration, which is the agency of United States of America. And I will also tell you how to make use of software which is developed by FAA for this design. Design of airport pavement is a complex engineering problem that involves the interaction of multiple variables, and FAA developed a software for the design of flexible as well as rigid pavements, and the analysis is based on layered elastic theory. This is the typical pavement section which shows different layers in the pavement, starting with the asphalt surface, which we call the wearing course, then stabilized base, which is generally bituminous base course like DBM. Then you can have a base course. This base course can be cement-treated base, lime-treated base, or normal base, and a sub base, a dredge layer above subgrade, and a layer of geosynthetic material if suggested by geotechnical and pavement engineer. FAA developed a software which is called FAARFIELD. Now FAARFIELD here stands for FAA Rigid and Flexible Iterative Elastic Layer Design Software. This is the full form of FAARFIELD. And this FAARFIELD is based on the maximum vertical strain at top of subgrade and the maximum horizontal strain at the bottom of all asphalt layers as the predictor of pavement structural life. It is similar to what we do in case of highway pavement also, as suggested in IS 37, that the maximum vertical strain at the top of subgrade and maximum horizontal strain at the bottom of bituminous layer should be within permissible limit. Now that is how basically it considers the strains. Now this is the wearing course, and here is the horizontal strain and stress at the bottom of asphalt layer. If your base course is also bituminous base course, then this will be below the bituminous base course layer. And here is the subgrade, and that is your vertical subgrade strain that should be within permissible limits. And the limiting values of these stress and strains are automatically calculated by FAA software based on the properties of the layers and aircraft characteristics. When all aircrafts are less than 60,000 pounds, that is the gross weight of the aircraft, that is 27,200 kg, it is suggested to use full depth asphalt pavement. And this software has the ability to analyze full depth asphalt pavement as a two-layer structure consisting of only the asphalt surface layer and a subgrade layer. But the preferred method of analyzing a full depth asphalt layer is to use a three-layer structure consisting of an asphalt surface layer on top of an asphalt base and a subgrade layer. FAA method considered physical properties of subgrade soil, and this method suggests classification of soil used in subgrade based on unified soil classification system as developed by US Army Corps of Engineers, and that is described in ASTM D2487. Now in this method, the soils are classified based on their grain size distribution and liquid limit and plastic limit. And based on this system, the soils can be classified starting from gravel to clay with high compressibility and peats. But the engineering property which is considered in the design is the CBR value. CBR value is considered on remolded sample, and E value is obtained by multiplying CBR by 10, a factor of 10. But in FAA software, the units are US customary units, that is in inch and PSI, and therefore E in PSI is 1500 into CBR. And FAA pavement design procedure recommends a maximum subgrade E value of 50,000 PSI, pounds per square inch, or you can say 345 MPa, that is corresponding to CBR 33 for gravel and gravelly soils, and minimum CBR is 5%. Base course: when aircraft in the design traffic mix have gross loads of 100,000 pounds, that is 45,359 kg, or more, then use of a stabilized base is required. Full-scale performance tests have shown superior performance of both flexible and rigid pavements that include base stabilized with asphalt or cement. Sub-bases used under stabilized base should exhibit a remolded soft CBR of at least 35%. Base or sub-base contamination. What FAA suggests that contamination of sub-base or base aggregate may occur during construction or once the pavement is in service. A loss of structural capacity can result from contamination of the base or sub-base elements with fines from underlying subgrade soil. Contamination reduces the quality of the aggregate material, reducing structural strength. And therefore, geosynthetic separation materials reduce contamination from subgrade when placed between subgrade and aggregate layer. But that should always be used with the recommendation of geotechnical engineer. Then comes the drainage layer. Now, drainage layers are recommended for pavements serving aircraft greater than 60,000 pounds, that is 27,200 kg. Constructed in areas with excessive subsurface moisture and where existing soils have coefficient of permeability less than 6 meters per day. Drainage layer facilitates the quick removal of excess moisture from the pavement structure. Proper outlets should be provided to ensure water is not trapped in the layer. Place the drainage layer immediately above the subgrade, except when geotechnical engineer recommends otherwise. Drainage layer is not a default layer in the FAA design, and therefore when you design the section, drainage layers are modeled as user-defined layers. Include a geosynthetic separation material when drainage layer is placed directly above the subgrade. The E-value which are suggested for different types of drainage layers are like this: for asphalt treated permeable base 150,000 psi, for cement treated permeable base 250,000 psi, and aggregate drainage layer which is unstabilized, that is your normal aggregate drainage layer, and E value will change from 15,000 to 30,000 psi. Higher value can be taken if it is supported by lab studies. When you use FAARFIELD software for designing the flexible pavement or rigid pavement, there are certain materials, standard materials for use in different layers. For example, for surface course, P501, P401, P403 and P404 are the type of material which are suggested in FAA for use in surface course. But you can certainly map these materials or these layers according to your specification. For example, here P501 and 404, they are for concrete pavement. This is PCC slab. Similarly, P401 and 403, they are asphalt mixtures. And E value of these asphalt mixtures in the software is assumed 30,000 MPa. In case of stabilized base course, 3-4 materials are suggested: 401, 403, 304, 306, 307. This 403 is to be used only when aircraft weight is less than 60,000 pounds. For base course, there are several materials: 207, 8, 9, 10, 11, 12 and 19. But some of these materials are to be used only when aircraft weight is less than 60,000 pounds, like 208, 210, 212 and 213. These are two materials to be used when aircraft weight is less than 60,000. And similarly, for sub-base course 154 and P213, and for subgrade 152, 155, 156. These are the materials which are suggested in different layers. Now here P154, for example, is exactly as given in clause 309 of MORT specification 2013. P155 is lime treated subgrade as per clause 402 of MORT specification. 152 is when construction is in embankment. 158 fly ash subgrade as per clause 403, and similarly you can draw parallel between these materials and MORT specifications. 209 is the crushed aggregate base as per clause 405 of the MORT specification. 304 is cement treated base, and 306 is lime concrete base course, that is your 601 in MORT specification, which is for rigid pavement. P501 is the PCC slab, 602 of MORTH. Use of P404 and P501 is recommended for locations that need a fuel resistant surface or a fuel resistant seal coat. And similarly, these materials can be used as stabilized base. There is a table here which suggests minimum layer thickness for flexible pavement structures. Asphalt surface, for example, should be 3-inch minimum when aircraft gross weight is less than 60,000 and 4-inch when it is more than 100,000 pounds. Now, when you say gross weight is basically operating weight, that is at the time of departure. Similarly, stabilized base is required when the gross weight is more than 100,000 pounds and minimum thickness should be 5-inch, 125 millimeter. And similarly for other layers. So these minimum thicknesses are automatically implemented in FAR software. Design with FAARFIELD software is based on the cumulative damage factor, in which the contribution of each aircraft in a given traffic mix is summed up to obtain the total CDF from all aircraft's operations in the traffic mix. The FAARFIELD analyzes the damage to the pavement for each aircraft and determines a final thickness for the total cumulative damage of all aircraft in the evaluation for each 10-inch wide strip over a total width of 820 inches. So the total pavement thickness is divided into 82 strips of 10-inch wide, and damage is calculated in each strip, and the CDF for the design is the maximum over all 82 strips. When the CDF sums to a value of 1 on any of the 82 strips, the structural design conditions have been satisfied. The CDF is calculated using this equation: number of applied load repetitions divided by number of allowable repetitions to failure. This is equal to annual departures into life in years divided by P by C, that is pass to coverage ratio into coverage to failure, or this can be written as number of applied coverages divided by number of coverages to failure. That is the CDF. Now what is this P by C ratio? This P by C ratio, an aircraft seldom travels along a pavement section in a perfectly straight path or along the same path each time, and this lateral movement is known as aircraft wander and is modeled with a normal distribution. As an aircraft moves along a taxiway or runway, it may take several trips or passes along the pavement for a specific point on the pavement to receive a coverage of one full load application. And the ratio of number of passes required to apply one coverage to a unit area of the pavement is expressed by the pass to coverage ratio, that is P by C. The number of passes an aircraft may make on a given pavement is easy to observe, but the number of coverages is mathematically derived in FAARFIELD software. ICAO suggests these P by C ratio for different types of aircraft. For single wheel, 5.18, for dual wheel, 3.48, tandem dual, it is 1.84, for Boeing 747 1.85, and for DC-1010 1.82, and similarly for other types of aircrafts the P by C ratio is defined. Now, payment design using FAARFIELD is a iterative process and there are 6-7 steps. The first step is you start the program, and after starting the program select a payment type. Then modify the payment structure by adding, deleting or changing the layers as required. Then create a traffic mix by selecting a stored mix or by picking aircraft from the aircraft library. There is the aircraft library in the software. You can choose the aircraft from that library also, or you can create your own mix of aircraft. If necessary, change the gross weight or number of departures of aircraft in the traffic mix. The design is based on tire pressure and tire width, and therefore when you change the gross weight, the tire pressure will automatically change. Then run the thickness design, run the compaction or life to obtain subgrade compaction requirement for new pavement construction, and then you can see the print of the design report. Now let me explain this procedure using a simple example. An example is like this: the design flexible pavement for an airport serving the following aircrafts: Boeing 737-800 with a gross weight of 170,000 pounds with the annual departure of 3,000. Similarly, Airbus 321-200 OPT, gross weight, departures. These are generic EMB 195 STD, CRJ 700. These are two different types of aircraft with their gross weight and their number of departures. And let's assume that the CBR of subgrade soil is 5%. So let us now first take some trial section, and trial pavement structure is like this: that the top layer is asphalt surface course of 4 inch, stabilized base of 5 inch, and we provide below that crushed aggregate sub base of 6 inch and a dredge layer of 12 inch, and CBR is 5%. Now with this trial section, let us go to FAARFIELD software and see whether this is safe or unsafe. If it is unsafe, then what would be the final payment section?
So you start the FAARFIELD software by clicking this icon here, and that is basically the software. Now you put a job name here, let us say a new design, and structure name, say demo, and select here payment type. This will be new flexible pavement, and we are here for thickness design, right? So now this is the default values and this is the structure: 4 inch of HMA, 5 inch of stabilized HMA, then a crushed aggregate layer of P209 of 10 inch. Now you can change this. You can change this, or you can insert a dredge layer here. Now in our design, we assume that 4 inch will be the top layer, 5 inch will be the next layer, and then you will have 6 inch of crushed aggregate base course and 12 inch of aggregate base. So let us select it and choose this uncrushed aggregate layer E154, add layer below. So a new layer will be added here, 154, 6. Now you can modify the thicknesses here, 4, 5 as per your trial design, 4, 5, and this is our 6 inch, and this will be 12 inch. And CBR in our design problem is 5, so take 5 here. So this will be E value now 7500, and these are default values of E for each of these layer material. Design life is 20 years. Now here it is always better, you see on the right side here, it is always better to calculate HMA CDF, so say yes, and automatic flexible based design, say no. Otherwise it will basically calculate, only iterate with this thickness layer. The next is to choose the aircraft. Now this is the aircraft library. Select the first aircraft The first aircraft in our list is B737, so let us say Boeing, and under Boeing you have 737-800. Here you just double click here, it will appear in this list here. Another one A321, so go to Airbus. A321 is here, A321-200 OPT, that is your aircraft. Third is EMB. EMB will be in regional or commuters. So EMB 195 STD, and another one is CRJ 700. Now these are the aircrafts. These are the aircrafts, and here you can change the gross taxi weight also, you can change departures also. But tire pressure and tire contact width, these will remain untouched. So in our case, annual departures are different from default values. So annual departure for, let us say, Boeing 737-800, in our example problem, it is 3000, so make it 3000. Now when you choose this aircraft, you can see the gear configuration also here. What is the distance between the wheels and what is the distance between the gear? Similarly, for this aircraft A321, the departures are 2500. For next, it is 4500, and last is 3500. Accordingly, it will calculate the total departures. Annual departures multiplied by design life 20 years, that gives you 60,000. Now with this, you run the program. The program is completed, and this is the final thickness is 4 inch, 5 inch, 6 inch, and 25.2 inch. Now this is the thickness design. If you want to see the structure, that is the structure now. Now in this step, FAARFIELD automatically computes a minimum required thickness for this P209 base layer. For practical reason, the design base layer thickness will be higher than the minimum. Minimum thickness for this is 6 inch, and that is what it has adopted here. So you can change these thicknesses as per your practical requirement or practical reasons. Say for example here, if you choose 4 inch, the top HMA surface, and this HMA stabilized layer is changed to, let us say, 8 inch, and this crushed aggregate layer, let us say 12 inch, that is your P209, changes to 12 inch, and last the uncrushed aggregate, let us say 10 inch. Now with this you get a 34 inch. Let us see the outcome here, run the program, and this is the final value which you got. That is 4 inch, 8 inch, 12 inch, 10.1 inch, and 34.1 inch is the total thickness of the pavement. If you want to see the structure report, now here is the structure report total. Just select this structure report here on the left side, and then you get the thicknesses, their modulus, CBR value, Poisson ratio, and so on. And this is the airplane information which you selected in the design, and that is CDF information. The total CDF will be 1, and HMA CDF is 0. This is subgrade CDF. Okay, so maximum strain at top of subgrade is critical in this case, whereas there is no strain developed at the bottom of the witness layer. Now if you want to see the CDF graph is here for your example problem. This is the CDF graph. Now the total, you have 4 aircrafts, and the contribution of each aircraft is shown here with different colors. CRJ 700 with yellow color. You don't see yellow color here, that means its contribution is very minimal. And similarly, EMB is a green color. This one is the critical aircraft. That is basically creating a lot of damage to subgrade level. The 737, Boeing 737 has a very little CDF value. Now the CDF graph basically it's a cumulative damage function versus lateral offset for each gear in the design traffic mix. And also a total cumulative CDF, this blue line. Now this, for a complete design, the peak value of total CDF will be 1. And the offset at which this CDF is, that is the critical offset. So this is the final structure report. So that is how we design a flexible airport pavement using the software FAARFIELD.